We're going to continue on here, chapter 14. Yes. Turn that around, writes better that way, probably. There you go. All right, so last time we were talking about the common ion effect. And sort of the idea of the common ion effect is much like the name implies. You have some type of common ion that is present within an equilibrium. And a lot of times this happens with weak acids or weak bases. So, for example, our acetic acid, when it goes in for a swim, will set up this equilibrium here of H plus and acetate. And if you have, say, acetic acid and you decide to also add in there a little bit of, say, some sodium acetate, which is a salt, and because that's a salt, it will 100% break apart into ions in solution. And because of that, it will create this common ion that's here. And this common ion will basically be essentially adding more acetate to that solution. The result of that is our friend Le Chatelier's principle would say that because we are now adding more of this acetate, it will cause the equilibrium to shift away from that side. And ultimately, what that's going to do is basically keep, for example, that weak acid together. If you did this, for example, with a base, it would keep the base together, a weak base together. And the end result of this in terms of sort of an acid is obviously it's going to stay together more, which means you will actually decrease the amount of H plus in that solution, and you will see the pH actually go up in that particular case. And that happens again also with sort of weak bases as well. So the presence of that common ion in that solution will cause really the weak acid or weak base basically to stay together more than breaking apart. And the result of that is it will have an effect on the pH. Here, for example, with a weak acid, we would expect the pH to be higher than it would be if the common ion wasn't there and you just had the weak acid by itself. In the case of a weak base, because it will shift equilibrium back towards the weak base side, away from the hydroxide side, we will lower our hydroxide concentration, increase our H plus concentration, so the pH of that weak base will actually be less than what it would be without the common ion present in that case. It doesn't mean that it would become like acidic or anything like that, nor does it mean like this acetic acid solution would become basic or anything like that. But in comparison, kind of like a calculation we did the other day, if you looked at I think the acetic acid by itself, it was like 2 point something, I think, and change. And with the common ion present, it was 4 points up. And so again, it was a higher pH because there is again going to be less H plus in that case. What we're really talking about here is really a buffer situation, and this is really where we do see this common ion situation occur, and buffers are pretty much that. A buffer, as we talked about, is made up really of a combination of one or two combinations. You will either have a weak acid and the salt of its conjugate base. And the salt really just means it's got something maybe like a sodium potassium. It's not really doing much, as we know, it's a neutral sodium potassium or something like that. It's really, the other part of it there. For example, this would be the salt of the conjugate base for acetic acid. So those guys, again, are Bronsted-Lowry partners. It makes it a salt because it has a sodium on there. It's an ionic compound. Again, the sodium really not doing anything but having a swim and not participating all that much in there. You could also have a base or buffer made up of a weak base and the salt of its conjugate acid. And again, remember that in a buffer, they both do need to be in the solution to begin with. That is essentially what makes a buffer. A buffer is the presence of both an acid part to the buffer and a base part to the buffer. And when you put something like acetic acid and some sodium acetate into a beaker, that acetic acid, once again, will set up that equilibrium along with the arrows in the beaker there. And we will have essentially as I mentioned before, sort of a base part to our buffer, if this is our buffer, obviously. And we will also have an acid part to our buffer as well. The purpose really and truthfully of why you add some, say, sodium acetate to it is that is a source of acetate, and that's going to kind of beef up the acetate concentration in that solution. So you have a really good amount of kind of both of those things in there to begin with. Ultimately, what a buffer is able to do, as we talked about, is prevent the formation of free H plus when you add acid, or OH minus when you add base. Now, they're able to do that because, again, in that solution, they have an acid part and they have a base part to that buffer, so that when you add an acid to it, it will react with the base part of the buffer and essentially tie up, if you want to think about it that way, the H plus from being free in that solution. And when you add a base, it will react with the acid part of the buffer and also tie up that free OH minus from being free in that solution. Remember, what affects the pH, right, is minus the log of the H plus concentration. And what affects the pH really is how much free H plus you got floating around, or free OH minus you got floating around. So by basically tying these guys up into something, it will allow really the concentration of H plus to stay relatively constant in both situations. And because of that, the pH will also stay relatively constant. Again, I say relatively constant, like I talked about last time. If you put a pH meter on it, maybe like what you're going to do today, you will actually see the pH move one way or the other, but we won't see really giant swings in pH when you add acid or base to your buffer if you made a good buffer. So remember that, when you make a buffer, or pretty much how it works, again, you have your acid part, which is sometimes just abbreviated as HA. A minus is the base part there of your buffer. When you add acid to it, it will react with the base part of the buffer. And what always happens in a buffer situation is you'll actually make the other part of the buffer. So you'll kind of use up some of the base part in this example here, and you'll actually make some of the other part of the buffer. Thank you very much. And what that does is it sort of kind of use up a little bit, make a little bit, and stuff like that. It allows it to kind of work pretty well. Again, if you added base in this case to this buffer, it would react with the acid part. You would then make more of the base part of the buffer, and it will use up a little bit of the acid part there, or HA of the buffer. Remember, we also talked about the idea that there is what's known as buffer capacity. You can definitely blow through a buffer if you're not careful, or if it's not necessarily made correctly for your situation. Again, as I talked about, technically speaking, if you just kept on dropping acid, you will eventually use up all of the base part of your buffer, right? And at some point, once the base part of your buffer is gone, it can no longer handle basically any more acid that you add. And if you continue to do that, you then will start to see a pretty big jump in pH, because now you're just adding a lot of H plus to that solution. So, they're not perfect, but you can make them really perfect. Also, a reminder that a buffer is not always a neutral solution. You can have a buffer, again, that's neutral. You could have a buffer that's acidic. You can have a buffer that's basic. You can make a buffer anywhere you like along the pH scale. And you can have acidic, basic, or neutral type buffers. When we do calculations for buffers, because they are a common ion problem, what happens is the concentration initially of your weak acid conjugate base or weak base conjugate acid remains relatively constant from initial to equilibrium, because it's staying together a lot more. There's not going to be a big change, which allows you, if you choose to do so in buffer situations, you could use the Henderson-Hasselbalch equation to solve it. And that is the pH is equal to the pKa plus the log of the base over the acid, where the pKa is equal to minus the log of the Ka value. Again, as I mentioned, sometimes people like to use this version of it when you're dealing with basic buffers, and it is slightly different, is the pOH is equal to the pKb plus the log of the acid over the base, where the pKb is equal to minus the log of the Kb value. Both the pKa plus the pKb will actually equal 14. So sometimes, again, that's a nice little way around it. As I mentioned last time, I would probably always roll with the Henderson-Hasselbalch equation, because pretty much 100% of the time, or at least 99% of the time, you're asked really what the pH is. So no sense kind of going this route where you got to still go 14 minus it. To get there, you might as well just go right into the Henderson-Hasselbalch equation. It will work for acidic buffers, basic buffers, neutral buffers. It doesn't matter. It will work for any one that you want. Now, again, as we talked about as well last time, if you are a fan and still like the ice table, you could absolutely still do the ice table like we did, I think, in that example, and it's perfectly fine. You do not have to use the Henderson-Hasselbalch equation, although it may actually save you some time, but you will get the same answer like we did in that example. The one big downfall sometimes that people have when they go to do the ice table in a buffer situation is they put a number here, they go here, and they always forget to put a number here. They put 0. So remember, you should have an initial concentration of your conjugate acid or base if you're doing the ice table and want to solve for the pH. Otherwise, as we talked about last time, if you zero this guy out, you're basically just doing a Ka weak acid problem and not a buffer problem. So you absolutely could still do an ice table, solve it like we've solved any of the ice tables before, and avoid the Henderson-Hasselbalch, or you could use the Henderson-Hasselbalch. They both, again, should give you the same answer when it's all said and done. We could also use the Henderson-Hasselbalch equation to figure out how to make a good buffer. And the way you could do that is, again, if you have equal concentrations of your base and acid, that will essentially give you the log of 1, which will essentially zero that out. And typically speaking, if you want to make a buffer, you would go to a Ka table and find a weak acid or weak base that has a pKa value. I guess I should have put the 1 in there, huh? Plus or minus 1 of your desired pH is sort of what you're looking for. So again, if you wanted to make a buffer in the 4-ish range of pH, acetic acid, again, is a really good one. If you wanted to make a buffer with a pH of 9, acetic acid is a really crappy choice to do that because it's not anywhere near what you want. A much better choice would be something like ammonia, and ammonium hydroxide or ammonium chloride would actually be a much better choice because it has a pKa value of around 9.25, which again is in the ballpark in that particular case. Any questions on any of that there? A reminder that in most cases we do use molarity when we go into here. But you absolutely can if you are using the Henderson-Hasselbalch equation because of the math of it. You could do moles and moles basically in that, and it'll all work out the same. So you can do that. If you're going to do the ice table, you probably should do molarity. Yeah, so if you're going to do the ice table, do it in molarity. But if you are going to use the Henderson-Hasselbalch, you could actually do it in moles, and it works out just fine as well because the volume on top and bottom essentially will cancel each other out and will work okay. Any questions on any of that there? Okay. All right, so as we can see here, in a non-buffer solution, we do see a very significant drop in the pH as we add some acid to it. Again, that is because in the non-buffer solution, like water that we talked about, you're just going to litter pretty much that solution with a bunch of H+. So the concentration of H+ is going to go up really, really quickly. The result of that is you're going to see a dramatic drop in the pH because the H+ went up and the pH will go way down. Again, when you add it to your buffer, what's going to happen is essentially that H is going to come over here to our acetate. It's going to get tied up in our acetic acid, And basically, you will still essentially have, that same equilibrium you started with. You won't have more H plus added to that solution in this particular case. You actually will have a little less H plus in there as well added in that solution, as it will basically be tied up. So with a buffer, we can see it will really maintain its buffer or its pH. It will not change all that much. Again, it will go down or up a little bit. And again, if you add that, you'll have just a little bit of H plus in there for a bit, so we'll drop it. All right. Which one of these or which one of the following can be a buffer? So take a moment and decide, can these things be a buffer or not a buffer? Okay, so let's take a look. So remember, as we just talked about, in order for something to be a buffer, you really need a combination, one of the two combinations. You need a weak acid and its conjugate base, basically, or you need a weak base and its conjugate acid. As we also talked about last time, why can you not have a buffer that is made up of a strong acid or a strong base? Why does that not work? Yeah, so if you have a strong acid or a strong base, it will 100% break apart, which means you won't be able to keep both parts of that buffer in that solution, the acid part and the base part. You'll just have like one of them, like the base part, no acid part, or vice versa. So we cannot have anything that is made out of a strong acid or strong base be a buffer. The difference, right, between these two things is our still Bronsted-Lowry definition of an acid and a base, and it basically is one H plus difference. So that's really the two things you want to think about when you look at a combination, if they could be a buffer, is are they basically partners, or are they just difference of one H plus? And is it a weak acid or a weak base involved? So when we look at KF and HF, this is HF, which is a weak acid. And by the way, I know that because by process of elimination, it's not one of the 6 strong acids we talked about. So again, knowing those 6 strong acids is quite important. This is KF, which is a salt, which really is K plus and F minus. And that looks related to each other by a difference of 1 H plus, and that would be his conjugate base. So I'm going to say yes, that would be a buffer in this case. Again, here the potassium is not doing much. It is what makes it the salt of its conjugate base. The true buffering power here is coming from the HF and the F minus, the HF being the weak acid and the F minus being the base part of the buffer in this particular case. Any questions on that one there? If I look at the next one, which is KBr and HBr. HBr is a acid. What type of acid is that? It is a strong acid, right? So can this be a buffer? No, that eliminates it right there, because when that HBr goes for a swim, it is going to 100% break apart into its ions, which means essentially all you got in that solution is like the conjugate base. And then you add some more KBr, which adds some more conjugate base to it, and you don't have an acid part to that buffer. And again, it's not really a buffer, so I guess you shouldn't call it a buffer. It will not be able to act as a buffer, and why it's not a buffer. Here, if we look at C, we got a little sodium carbonate and a little sodium bicarbonate in this particular case. Really here, the sodium is just some spectator ions. So if you scratch out the sodium and rewrite what you're left with, you're basically left with these two guys. These two guys related to each other. They are. The only difference is 1 H plus, which is what you need for a buffer. This also comes from carbonic acid, which is a weak acid. Again, not one of the 6. So that is what comes from it as well. And this would be a buffer in this case. By the way, which one would be the acid in this case of the buffer? Which one's the acid part of the buffer? Yeah, it's got the H, right? So it's got to have the H to give. This one does not have an H. That would be the base part of this particular buffer in this case. Any questions on that there? All right, so let's talk about, now we talked about buffers, let's talk about calculations and determine the pH of a buffer. So first off, let's do part A, or why don't you do part A? Calculate the pH of a buffer that's made up of 1 molar acetic acid and 1 molar sodium acetate. So Ka value there for acetic acid is on the bottom, 1.8 times 10 to the minus 5. So what would be the pH of this buffer that you made and will make in like an hour, maybe? Okay, so let's take a look. So first off, the problem did not say that it was a buffer. You need to be able to recognize it because not all problems will tell you it is a buffer happening here with flashing lights. So again, when you look at it, you should hopefully be able to recognize that these two things are related to each other. And again, really this thing is Na plus and acetate, which again, if you look at this guy and this guy, the only difference there is 1H plus between them, which makes it really a buffer. By the way, not one of our 6 strong acids, so I know it's a weak acid. I also know it's a weak acid because there's a Ka value, right? So that tells me it's a weak acid, and that gives me all that information. Once you identify this as a buffer, you really do have 2 options. You can roll right in to the Henderson-Hasselbalch equation, which again may be the easiest move. You could also do an ice table. So again, it is your preference. If you chose to do an ice table, you would do it just like a weak acid problem, where our weak acid would break apart into H plus and acetate. And again, as we've been talking about, the important thing here is you would have 1 molar there, you would have 0, and you would definitely, once again, need that initial right there. Otherwise, you are not doing the correct problem that you're supposed to. You would go with your x's like normal, and that would get you 1 minus x, x, and 1 plus x. Again, this would go into our Ka. We would solve for x. X in this case would equal the H plus concentration. And then you could go obviously into the pH equation if you wanted to. Now, perfectly fine if you want to do that, you will go that way. I'm going to choose in this case just to go through the Henderson-Hasselbalch equation. I will need the pKa value. So the pKa is going to be minus the log of the Ka. That is minus the log of 1.8 times 10 to the minus 5. That's a 4.74 pKa. Putting in our numbers then, our pH would equal 4.74 plus the log. In this case, obviously that is my acid and this is my base in this case, right? And that would give me 1 divided by 1, which would get me 0. And we would open up this buffer here with a pH of 4.74, which would make it an acidic buffer and the most popular buffer ever used in examples, yes. Yeah. For the equation. So really, you would probably in this case, since this buffer is made up of a weak acid and its conjugate base, you would want to use the weak acid and do it like a Ka problem. Now, if you had a buffer that was made up of like a weak base and its conjugate acid, you would probably use the weak base and set it up like a weak base type problem, and like we did previously in the last chapter, and do that one. Yeah. Other questions? Okay. All right, so that is our buffer here opening up here with a 4.74. What we're going to talk about now is what happens when we actually add something to our buffer. So we have a buffer sitting there. We're going to add some acid or base to it for the funsies and see what happens, right? And we want to know how that's going to affect the pH. So a first couple of things we want to think about, for example, is we have my buffer floating around in here, which is my acetic acid and a little H plus and my acetate, right? And these guys have molarity in that solution moving around. And let's just say I took some HCl or sodium hydroxide or whatever it may be, and I add some more volume to it. Does the molarity stay the same or does it change for my acetic acid and my acetate and everybody in there? It does change, right? Because molarity is moles of solute divided by liters of solution. And basically, when you add more solution, the bottom part changes. So when you add more volume to something, what happens is the molarity continuously changes. The thing that actually stays the same is the moles of solute. That stays the same regardless of what you put in there. And by the way, the moles of your buffer that you have in that solution is pretty much what you have in there to keep it as working as a buffer. It is actually the moles part that actually works there. So when we add volume to volume, we want to make sure that when we do, for example, an ice table, we should actually do it in moles, not molarity. And you want to do the ice table in moles, not molarity, because again, the molarity would be constantly changing as you add the volume to it. So you will do an ice table in moles. After the first ice table, I highly, highly recommend that you should convert those moles back into molarity after the first ice table. Because in 9 times out of 10, if you were going to continue on with those numbers, you're going to need it in molarity and not moles. And that's, again, a common mistake that happens a little bit later on along the way when we do some calculations. So if you're adding volume like you do here, like you have a buffer and you decide to add more acid to it or more base to it, you need to figure out how the buffer is going to change based on how much acid or base that you added to the buffer so that you can calculate the new pH of your buffer at that point. And it should be done in moles and then converted to molarity at the end. This also occurs as we'll talk about when we talk about titrations, right? Because in titrations, you're doing nothing but continuously adding volume, which means the molarity is continuously changing, but the moles aren't. So you have to do that in moles. So let's take a look at B together and see how we're going to do this. So what we want to know in this particular case is what is going to be the pH after we add 0.1 molar HCl to it. In this particular example that we're going to do right here, we're just going to make the assumption that everybody stays 1 liter, just to kind of keep the numbers the same. Not always the case. You do have to calculate the moles of everybody, but just to make this first example a little bit easier, we're just going to assume that nobody's volume changes. Everybody's just 1, but normally you would need to figure out the moles. By the way, we figure out the moles, right? Because moles is liters times molarity, right? So that's the way we would normally figure out the moles. All right, so let's see what happens here. We're going to take our same buffer here. We got our 1 molar acetic acid along with our 1 molar sodium acetate. And it has the same Ka value, 1.8 times 10 to the minus 5. And again, we're going to add 0.1 molar HCl to it. Again, in this case, we're going to assume everybody is 1 liter, basically. Everybody has 1 liter volume. All right, so the first thing that's going to happen in this case is we have our buffer moving around in our beaker. And again, we have the acid part of our buffer and we have the base part here of our buffer. Now, when I add some HCl to this mix, that is basically going to give me some H plus coming in and some Cl minus, basically dropping into the solution. So when I add HCl to this buffer, will it react with the acetic acid or will it react with the sodium acetate? It will, because they're called acid-base reaction, not acid-acid reactions. It sounds funny, right? So this is my acid, right? That's my base part of the buffer. So when I do that, we're going to get a reaction with the base part of the buffer, which is the sodium acetate. This is frankly just going to do a double displacement reaction, right? Plus minus, plus minus. We're going to switch partners, basically, right? And we're going to get We got their little sodium chloride there. And we're going to run into my beaker. That's not good. We're going to erase my beaker there. There we go. All right, so and obviously here we will make acetic acid, right? Which is our part of our buffer here to begin with, right? So what we want to see in this particular case is what's going to happen to our buffer when we add this HCl to it. So we do need to do this in moles, and in this case, for our HCl, we're going to assume we have 1 liter. So 1 liter times 0.1 molar will give us 0.1 moles of HCl. Also, for our buffer here, we have 1 liter of it, which means for my sodium acetate, 1 liter times 1 is 1 mole. We have 0 here. And for my acetic acid, we also have 1 molar times 1 is 1 mole for this. Remember, also messed up a lot by people is right there. People will zero this out over here, which means you're not doing a buffer at this point. So you again do need to have those initials on both sides for it to be a buffer. All right. Now, a little bit different than ice tables we've done up until this point is if I made this buffer and everything's working correctly, should I still have HCl left over when it's all said and done? The answer is no, right? Because that's the purpose of the buffer, which is to basically kind of use up all that HCl. So in this type of ice table, we actually know the change that's going to happen. We don't actually have to solve for X. We actually know what it's going to be. It should use up all of my acid I'm adding to this buffer. So this should be minus 0.1. This should be plus, no, still minus 0.1 moles. And this should be plus 0.1 moles as I go through there. So slightly different, and typically speaking, if you're doing an ice table with moles, you will actually know the change part usually. So you'll usually know the number it should be. How do I know which one to choose? Well, you should always choose, in this case, the acid or base being added to the buffer. But logic should also tell you that if I chose the larger number as my change, what type of number would I get as I subtract? I would get a negative number, right? And you can't have a negative concentration. So I'll tell you this now and I'll tell you it later. Resist the urge you're going to have to choose the larger number. Yes, because there will come a time as we get to a calculation where you want to choose that larger number. Don't do it. You should never have a negative number at the end here. So again, it happens a lot. People just want to choose that number. So this is going to be 0, and clearly I'm going to get my calculator out because that's a lot of math to do right now. 0.9 moles at this point. And again here, we want to remember we're actually adding in this case. So 1.1 moles at this point. First off, any questions on this ice table here? Now, as I mentioned before, because we're adding volume, we do need to do this ice table in moles. You should always, at this point, it's really good practice, convert these moles back to molarity. In this case, what you would be dividing by is the total volume. That would be the volume of the buffer you started with and the volume, in this case, of the acid we added. In this particular example, though, we're just keeping everybody at 1 liter to make everything nice and easy. So we will divide by 1 liter. But again, normally this should be your total volume, and that would be your buffer plus whatever you added. Yeah. So that is what it should be. Obviously, it should be in liters as well, right? To get everything correct. That would give you 0.9 molar and 1.1 molar in this case. Any questions on that? At this point, if you're not sure what's going on, your ice table could actually help you as well. If you look at the ice table, you have basically this guy left over and you have this guy left over. Those two things, by the way, are still a buffer, right? I still have the weak acid and the conjugate base left over, and it is still a buffer. By the way, why did I ignore the sodium chloride here? Yeah, it's a neutral salt, so best not to put anything there so you don't try to use it incorrectly, right? So no need to put anything there. Because this is still a buffer, that means I could do one of two things. I could go into the Henderson-Hasselbalch equation at this point, or you could do a second ice table if you're again fond of the ice table. The second ice table would be this ice table with your equilibrium concentrations as your initial. So you would do the same type of ice table we did in part A if you did the ice table in part A, and you could use these equilibrium guys as your initial concentrations. I am again going to go into the Henderson-Hasselbalch equation. And again, it's going to be the same pKa we had previously, 4.74. The log of my base, and which one's my base again? It is the sodium acetate. So that would be 0.9 divided by 1.1. And we are going to get, in this case, hopefully a buffer that works well. Let's see. A pH of 4.65. Yeah. Again, you could do the ice table and you should get the same pH at the end there. Question on that there. Now, did our buffer do good? Our original buffer had a pH of 4.74. We added some acid to it. It went to a pH of 4.65. That is not a giant jump in pH, right? So our buffer worked pretty well. Did my buffer at least move in the correct direction based on what I added? It did. I added acid, the pH went down. So if you did this calculation and your pH went above 4.74, you went the wrong way in this situation. So again, these are things you want to think about as you're doing the calculations. Question on that there. All right, well, I tried one. Why don't you try one? Let's see what we got here. Let's do I want there. That's what it is. We'll do the KB here for NH3. Why not mix it up? 1.8 times 10 to the minus 5 in this case. Yeah. Why not? All right, so we have a solution that is 0.3 molar ammonia and 0.36 molar ammonium chloride. What is the pH before and after you add 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of this buffer? In this particular case, we are not keeping the volumes constant, so you need to kind of figure that stuff out along the way. So we're looking for two answers here, pH before. Okay, so let's take a look. So once again, if it didn't tell you it was a buffer, you hopefully should be able to recognize it. Here we have NH3, and this is ammonium chloride, which is essentially NH4 plus and Cl minus, and we have NH3. Our buffer components are these two guys, as they are related to each other. We also know here, in this case, I gave you the Kb instead of a Ka. That means that is a weak base and is conjugate acid in this case, right? And because that's a buffer, one of the first questions is we want the pH of it before we do anything. So again, you can either do an ice table if you choose. On this one, you actually have two options if you want to do an ice table. You could do NH3 using the Kb like a weak base type problem. You could also get the Ka value for NH4 plus and do a weak acid ice table as well. They both will come out the same. So you do actually have a couple options in this particular case, which ice table you want to do. I'm going to do the pH, and again, I'm going to actually use the Henderson-Hasselbalch equation. This also would be one where people would perhaps want to use this version of it, but once again, I'm shooting for the pH here, so I'm not going to use this version in this case. I'm just going to use this one. Now, when I do use this one, which is the Henderson-Hasselbalch equation, I need the pKa value and not the pKb value. So again, you have a few options. I could use Kw like we did previously, 1 times 10 to the minus 14, and divide it by 1.8 times 10 to the minus 5. That would get me 5.6 times 10 to the minus 10 as my Ka. I then could put it into my pKa value here, minus the log of the Ka, and that's going to get me something, 9.25 perhaps. 5.6 to the minus 10, 9.25 as my pKa value. Now, you could also have converted this into the pKb. You then could have used pKa would equal 14 minus the pKb, and that's perfectly fine as well. I will say in this particular example, based on rounding, you might get 9.26 as your pKa because of rounding, and that's okay in this case. But again, you could have went that route to get to the pKa value as well. And again, the third route was just go right into here, I guess, with the pKb value, and you could have done that as well. So we have our pH. I can go with 9.25 plus the log. Again, we want to make sure we get the base over the acid. Once again, the NH3 here is our base, so that should be 0.3 over 0.36. I can use the molarities here because I haven't added anything to it, right? I'm just looking at what the pH of the buffer is. We haven't added volume. And if you do that, we will open up with here a pH of this buffer of about 9.17. That's our opening pH here. First off, any questions on that particular one? This is obviously a basic buffer, works fine with the Henderson-Hasselbalch equation, as you can see. You just need to make sure you're using the pKa value in it and the base on top, acid on the bottom. Any questions on that one there? All right, we're now going to actually add to this buffer some solution here. So to this buffer here, we're going to add, basically what we got going on is we have 80 milliliters of our buffer. And that's our NH3 or NH4 plus and so forth here. And we're going to add to this some sodium hydroxide into here. So because we're adding volume in this particular case, we do need the moles like we talked about. So we are going to have to do an ice table. Really, the purpose of the ice table is to figure out how your buffer changed after you add, in this case, excuse me, the sodium hydroxide. But to do that, we do need everybody in moles. So this case, the volume was not held constant. So our moles of sodium hydroxide would be, we need to convert our volume into liters, 0.02 liters, times our molarity of our sodium hydroxide, 0.05 moles per liter. The liters will cancel, and that will give us our moles of 0.02 times 0.05, 0.001 moles. We'll do it for our buffer. And now sometimes people are confused, but the 80 milliliters is both of those things together. So that is the volume for both parts of the buffer because they're all together in the same beaker. So the moles of the NH3 would be 0.08 liters times the molarity of the NH3, which is 0.3 moles per liter. Again, the liters would cancel, and that's going to get me 0.08 times 0.3, 0.024 moles. And lastly, the moles of the NH4 plus in this case. The Cl minus here is a neutral salt, right? And it's just hanging out as a spectator ion in this case. Again, we have 80 milliliters of that buffer, and the molarity of that guy is 0.36 moles per liter. Liters again will cancel, and that's going to get me there 0.0288 moles. Yeah, what's up? So what we're looking for is in the case of the ice table and the initial and the moles of that is initially how many moles of each of those went in there. And for the buffer is really it was only 80 mils of the buffer to start with. And it's really that would give you so many moles of the NH3 and NH4 plus that's floating around. And that's kind of like your initial starting moles of it. And the same thing with the sodium hydroxide, before they get mixed, right? That would be your initial moles. That's why we wait till the kind of the end of the ice table to divide it by the total volume at that point. That would then give us the molarity of everybody that's in the mixture altogether after it's reacted. Yep. Other questions? All right. So we got everything we need here except for room on the page. So just do that. Must try that move maybe. All right. All right. Now let's remember what we're doing here. So we're adding some sodium hydroxide here, right? And when we add sodium hydroxide, it's going to react with the NH3 or the NH4 plus. Yeah, that's the base sodium hydroxide. It's going to react with the acid part. It's your call. I'll leave the chloride in there if you want. You can take it out, whatever you like, however you feel good about it, I suppose. Really a double displacement sort of thing happening here. We're going to actually get a few things going on, believe it or not. We are going to get some sodium chloride, which is not so important. We will make, obviously, the other part of the buffer, which is the ammonia. And dare I say, we will even make a little bit of water there as well. So we'll have like a 3-pack of stuff sort of made on the other side as the sodium and the chloride will come together. And really this acid is going to donate that over there to the hydroxide, the H plus. We get all that. So here we're going to use our moles because again, we're adding volume. So sodium hydroxide, we had 0.001 moles we calculated. Our NH4 plus, I hope it was this number. I think it was moles, 0.0288. And our NH3, we had 0.024 moles, if I'm not mistaken. Should I even worry about the sodium chloride or the water in this case? No, because water is not going to mess up the pH and sodium chloride is still neutral. So again, no need to really mess with it. Now, because this is a buffer, I should know my change. The change should be which number here? Should be the moles of sodium hydroxide, right? Because that's what a buffer hopefully should do. This is going to be minus 0.001 moles, minus 0.001 moles, and plus 0.001 moles. Feel like I added an extra zero. No, I didn't. All right, that's good. And that's going to give me 0. We are going 0.0288 minus 0.001. Going to get us 0.0278 moles. And again, on the other side, we are adding, not subtracting that. So we're going to add that, which would get us 0.025 moles. First off, any questions on the table here? At this point, to answer your question, as we were talking about earlier, this is the point where we do want to divide and bring everybody back to molarity using the total volume. And as you correctly said there, we started with 80 mils of the buffer and we added 20 mils of the sodium hydroxide. So that's going to give us a total volume of 100 milliliters. So we are going to divide each of these guys by 0.1 liters to convert it back into molarity at this point. 0.0278 divided by 0.1. I'm just going to move over a little bit there. 0.278 molar and 0.025 molar on that particular one as well. At this point, if you are not sure, and I put an extra 0 there, that's not so good. Let me get rid of that extra 0. I was talking about earlier, put one there. All right, let's get that there. 0.250. There we go. So as we were talking about before, at this point, if you're not sure what's going on, you really should not overlook your ice table because it can definitely help you. And in this particular case, what we have left at this point is this guy, and we have this guy. And again, hopefully you can still recognize that is a buffer. And that again is going to help you determine the pH. which, as we talked about, you got a few options still to do this. I'm going to go Henderson-Hasselbalch. You can absolutely still do an ice table if you wanted to at this point. So pH is equal to the pKa plus the log of the base over the acid. That's going to give me the same pKa we used previously, 9.25, plus the log of our base, which is the 0.250, divided by our acid, 278. And going to give us a 9.20 as our pH, in this case, after we add the sodium hydroxide. First off, question on that. Did our buffer do well? Let's see. We started out at 9.17, right? Before we added the base. We added the base and it jumped way up there to 9.20. Not a big jump, right? So that's good. The buffer worked really well. It also, again, did move in the correct direction. We added base. We would expect the pH to go up a little bit, right? And again, these are things you want to think about as we talked about. Any questions on any of that there? Let's try another one here just for fun. Why not? Let me just make one up and hope for the best. All right, we want to know what is the pH of a solution made of 0.4 molar HF and 0.6 molar sodium fluoride. The Ka for HF, 6.5 times 10 to the minus 4. And then we want to know what is the pH after we add. I changed my mind. I'll go with this one. Why not? 15 milliliters of 0.5 molar hydrochloric acid to 60 milliliters of this buffer. So since we're getting to the end here, and it'll probably be helpful for lab as well, so let's go through it here together, see how you're at least progressing on it. So again, we do know this is a buffer, even if it didn't tell us. These two guys are related to each other, as we saw earlier. We got F minus really, and HF. I know that is a weak acid, so we do have a buffer. So again, just to get the initial pH of the buffer by itself before you do anything, probably the easiest move is just to go into the Henderson-Hasselbalch equation. Again, you could do an ice table if you wanted to. We will need our pKa value here. So in this case, our pKa will equal minus the log of the Ka value, 6.5 times 10 to the minus 4, minus the log 6.5 to the minus 4. So that's going to give us like a 3.19 perhaps as our pKa value. And to get our initial pH of our buffer here, we'll go 3.19 plus the log. Again, the F minus or the sodium fluoride is our base, so 0.6 over 0.4. There it is. And that's going to get us 0.6 divided by 0.4. Take a little log action of it and add a 3.19 to it. Going to give us an opening pH of 3.37 here as our opening pH. Any questions on that one there? Now for the second part, we're going to take this buffer basically and we're going to add some acid to it. So that automatically tells you you're adding volume. So you do really need to do an ice table to figure out how the buffer is going to change. And you need to do that in moles as we talked about. So really that's the first thing I'm going to do here is just get the moles of everybody. So for my HCl, we're going to take 0.015 liters, which is converting our volume into liters from milliliters, 0.5 moles per liter. That's going to get me 0.015 times 0.5. Probably helps if you put the right number in there. 0.015 times 0.5. That looks better. 0.0075 moles of HCl. We also need the moles of everything else there. So why not sodium fluoride moles? We'll go 0. And we have 60 milliliters of our buffer. So 0.06 liters times the molarity of our sodium fluoride, 0.6 moles per liter, so they cancel. That gives us 0.06 times 0.6, 0.036 moles of our sodium fluoride. And lastly, our HF moles. Also, same beakers, same amount of volume, 60 milliliters converted into liters, times the molarity, 0.4 moles per liter. Again, liter is going to cancel. 0.06 times 0.4, 0.024 moles of our HF. Any questions on those calculations? All right, now we need to do the ice table. So here we're adding some HCl, which is an acid, which means it really should react with the base part of our buffer, right? Going to do basically a double displacement reaction. Again, if you're not sure what you get on the other side, one thing you should know is you should always get the other part of the buffer. So that's pretty much for sure what you're going to get. And in this case, we'll get some sodium chloride in this case. We are going to do this in moles. So if I don't clear my calculator, maybe I'll remember them. 0.0075 moles. Our sodium fluoride, I believe, was 0.036 moles. And our HF, 0.024 moles. Once again, we need that number. Otherwise, we're not doing the buffer problem. So super common error. Change is going to be our HCl moles in this case. So minus 0.0075 for both of those. We're going to add 0.0075 moles. That is going to get us here 0 for our HCl, 0.036 minus 0.0075, 0.0285 moles. We are adding on the other side there 0.024 plus 0.0075, 0.0315 moles. Any questions on the ice table? Ignoring sodium chloride for the reasons we've done previously, not going to affect anything. Here we want to go obviously back into molarity. So our total volume, we added 15 milliliters of the HCl to 60 milliliters of our buffer, 75 milliliters looks like. So we're going to divide everybody here by 0.075 liters. That's going to give us a couple of concentrations here. 0.38 molar and 0.0315 divided by 0.075, 0.420 molar. Once again, if you're not sure, this is all you have left in your ice table, which again, you should still recognize as a buffer. So again, at this point, ice table are back into Henderson-Hasselbalch pKa plus the log of the base over the acid, 3.19 pKa. Yeah, I hope. Plus the log. Once again, our base is this guy, 0.38, 0.420. See how bad I did with my made up numbers. Let's see. We end up with a 3.15 pH. After we added acid, we started with a 3.37. Not too bad. We're making up numbers, I suppose. Any questions on any part of that there? So again, buffers, you have a variety of ways to solve it, ice table or Henderson-Hasselbalch. One final note on the Henderson-Hasselbalch, as I mentioned last time, it should only be used in buffer situations. So do not use that equation in other situations or you will get it wrong. Any questions?